Okay, we are doing section 6.2 today. Okay, we are starting. We're going to focus on linear second order. Homogeneous equation. We have a linear second order homogeneous differential equation with standard form like this. I just have a bunch of terminology that we have to actually take care of, okay, at the beginning, before we actually do examples. So what is an ordinary form? Ordinary form of this differential equation is that if the px and qx are analytic at x0, then what is analytic? Analytic, that means it's essentially means it's a very smooth function. That means you can differentiate differentiable infinite number of times. That means you can take the first derivative, you can take the second derivative, and you can take the third derivative. You can keep differentiating and it still makes sense. Okay, and that's called analytic. Essentially, it's a function that is very smooth. You don't have to worry about it too much. I mean, it's just some technicality here. Okay, so for example, I can have a function like if I have a function f of x, let's say equal to x to the power 1/2. Okay. Maybe not 1/2. The example I have is maybe let me see what my example is here. Probably it's like x to the power 1/3. Okay. If you, this one is still pretty smooth. I mean, if you keep doing f prime x, negative 1/3, x to the power negative 2/3, and if you keep doing this eventually the function is not going to be differentiable at x equal to 0 because some of this function, for example, this guy here, 1 over, so x to the power 2 over 3. This one is going to be not continuous at x equal to 0 because when x equal to 0, this guy is going to blow up. Okay, so this guy is continuous at x equal to 0. So fx is not analytic. Don't worry about this technicality too much, but I do have to go over it because of the terminology. Okay. So there's a theorem which we are not going to prove, but based on the theorem, that the theorem justifies the methodology that we are going to use. Okay. So this is the theorem. We say that if x naught is an ordinary point, okay, ordinary point is defined here, then there are two independent solutions, okay, of this form. It basically justifies that you're going to have a power series solution, okay? Any questions so far? Any question?
Sorry, Professor.
Yeah.
Sorry, Professor, I didn't get the definition of the ordinary point.
Oh, so, sorry, I just look at the chat and I have a mistake here. Yeah, okay. So the definition of ordinary point. Ordinary point is a point, okay? It's a point where both px and qx behave very nicely, okay? Because px and qx are some functions, right? There are some functions. The function can be, it can look like this. Let's say px can be, px is like x to the power 1/3, x to the power 1/3 like this. But this function is not analytic, okay? That means it doesn't behave nicely enough. Behave nicely means very smooth. How do we talk about a function being smooth? It has to be continuous, okay? But not just continuous, it has to be differentiable. Not just differentiable, you can, after you differentiate once, you can differentiate again and again and again, it still makes sense. This x to the power 1/3 look like it, did I draw it right? Probably didn't draw it that way. X to the power, I draw x to the power 3. It's the other way. X to the power 3 is like this. X to the power 1/3 is more like this. Okay, it's kind of smooth. But if you differentiate a couple of times, it's going to be, it's not even continuous at this point. Because this guy actually has, at this point here, the slope is infinity.
Gotcha, thanks.
For this function x to the power 1/3, the slope at x equal to 0 is infinity.
Cool. Thank you.
Okay, so that is not considered very smooth. It's considered not considered very nice. Okay, so in that case, x equal to 0 is not an ordinary form. Okay, so it's saying that if these functions behave nicely enough at that point, then there will be, you are going to have power series solutions. Okay, at that point, this is a power series of the solution center at the point x0. You guys remember we did power series in calculus 2. So this will be a power series center at x0. Okay. And we actually talk about radius of convergence and all this stuff. That means around there, around the point x0. Okay. Then this guy is going to approximate the solution of the actual converges around x0. Okay, and x equal to x0, then this guy, the whole thing becomes 0. The output. That's it. Any other questions related to this? You guys remember a little bit about interval of convergence from calculus 2? The interval of convergence is centered at x0. Okay, if not, any other question? I'm going to continue that. These are technicality, okay? So I do have to go through this because the terminology. So this is basically saying is that if the functions are nice enough at that point, then we will have power series solution. Okay, centered at that point. Okay. I'm going to just continue that. Once I start to do example, you will be better. We are going to focus on x not equal to 0. When x not is not equal to 0. Connor, say that again. What did you say?
Never mind.
I did not hear you.
Never mind. Sorry about that.
That's okay. So we are going to focus on the case where x not equal to 0. The other case are similar. Okay, you have to modify a little bit. Okay, so I think it's probably better for me to just start to do example. That may be the best. Okay. Okay, so the ordinary point is 0. That means this power series is going to look like this. So the solution is going to look like this.
Also, Professor, For
Yeah.
the theorem, isn't it plus q of xy rather than just plain q of x?
Q of xy. Thank you.
Yes.
Thank you so much. I appreciate that. Okay, solution has this form. So we'll go through the same procedure we have done before, okay? So we start out with this, y equal to this. So what will be y prime? You take the derivative of this. Do you guys follow this step?
Yeah.
When I take the derivative, one of the term, the constant term goes away. Is it okay? Yes? What will be y double prime? Do you guys still follow? So y double prime plus x times y, okay, equal to 0, right? That's what you say. So what does that mean? That means this guy plus x times y. Let me know if I make a mistake. This guy here, this x here can be moved over here, and you end up adding 1. Are we still good?
I didn't catch the first part. You said we're just taking the derivative, correct? The first part, yeah, right there. Just taking the derivative, right?
The constant term goes away. When you take the derivative again, that constant term goes away. So that's why it changed from, it's from 1 to infinity, and here it's from 2 to infinity.
Yeah.
Okay. Now we are going to line this up by doing some replacement operation. Okay. How do I do that? You replace n by what? For this part? From here to here will be replace n by
N plus 2.
replace n by
N plus 2.
n plus 2. How about this part here? Replace n by
M plus 1.
Professor, is that an n plus 2 or n minus 2 that's circled? in red.
Minus.
Minus. Okay.
So replace n by n minus 1. Are we still okay?
Professor,
Do you
why
say
do we change that second term?
why are we changing the second term?
Yeah, to n plus n minus 1.
Because
Why
I want this to be n for both of this. I want both of them to be n so that I can combine them together.
okay.
So this guy I can replace it by n equal to 0. This one I can replace it by n equal to 1. Okay. So I have this now. I'm combining both of them together. Now, this guy start with n equal to 0. This guy start with n equal to 1. Okay. So I have to take the first term out. This guy. If I take the first term out here, n equal to 0. What happens when n equal to 0? N equal to 0, that guy will be 2 times 1 times
C2.
times C2 plus sum n equal to 1 to infinity of this whole chunk of stuff. Plus do you guys follow that?
Yes.
Okay. Everybody else okay?
Feeling good?
Okay. Now, you have to understand that this is a constant term. When n equal to 1, you have the x term. N equal to 2, you have the x squared term. What this means is that the right-hand side is 0. So all the coefficients are 0. So 2 times C2 is equal to 0. Okay. And then these guys, this particular thing, okay. So this becomes C2 equal to 0. Cn plus 2 equal to negative Cn minus 1 divided by n plus 2, n plus 1. Okay. Or n equal to 1, 2, 3, 4, and so on. Okay. And this is called the recurrence relation. Any questions so far? Okay. Now, in order to start this recurrence relation, okay, I'm going to assume
Professor, is there a reason why you selected the n?
Shelby, I cannot hear you. There's this noise there. What are you saying, Shelby? Shelby? Okay. Now, I'm going to explain to you later what this is, why we do this, okay? For now, can you just accept it for now? Let me do the computation, okay? Yeah. Okay. I'm going to assume C0 equal to 1 and C1 equal to 0, okay? And then I will compute all the C's. On this the other side, I'm going to assume C0 equal to 0 and C1 equal to 1, and then compare all the C's. I will have to explain this to you later, okay? Why this will work, okay? If I continue like this, I'll get one of the solution. I continue like this, I'll get the other solution. But that needs some explanation a little bit later, okay? So, based on these formulas, now if I have C0 equal to 1, C1 equal to 0, now I already know C2 is equal to 0. So what will be C3? Why don't I just do it like this? Okay. C0 equal to 1, C1 equal to 0, C2 equal to, oh, I already know C2 equal to 0. Okay, so this formula is saying that, C3 is related to C0. Can you see that? When n equal to 1? When n equal to 1?
Yeah.
1, C3 is related to C0. It's minus what? Minus C0. C0 is 1 divided by, this is for n equal to 1. This guy is for n equal to 1. 1 plus 2 is 3. 3 and 2 is 6. Is it okay? Do you guys understand how I get C3 equal to negative 1 over 6? Do you guys understand how I get negative 1 over 6?
Yes, I understand.
Plug n equal to 1 into here.
Mm-hmm.
Yeah.
Okay. And then here, the next one is going to be C4. C4 is going to be n equal to 2, okay? C4 is going to be related to C1, but C1 is 0. So this guy is 0. Can you see that? The next one is C5. C5 is n equal to 3, related to C2, but this guy is 0. How about C6? How do I do C6? C6 is related to C3. It's negative for this guy, which is 1/6. Divided by what? Divided by 3 and equal to 4. And equal to 4, 1/6 divided by 6 and 5. Okay. Are you guys still following? 1/6 times 6 times 5. Okay. I can just multiply out. What is 6 times 6 times 5? 180. What would be C7? C7 is related to C4. What would be C8? Okay. It's a lot of detail, but are you guys following this?
Yeah, it's pretty easy.
Okay. What would be C9? C9 is related to C6. So it will be negative 180 over 11 times 10 will be 11 times 10 negative 19800. And you can keep going, okay? C10 is 0, C11 is 0. Okay, so one of the solutions, so you have two fundamental solutions. One of them is called Y1. It's actually this guy with these coefficients. Okay, now remember originally we say that the solution has this form, right? Okay, you have two solutions, both of this form. So y1x will be 1 minus 1/6 x cubed plus 1 over 180 1 over 180 x to the power 6 minus 1 over 19800 x to the power 9. And you can compute as many terms as you want. Okay? You can come. I mean, there's no really nice pattern. There is a pattern in this case, but I mean, it's kind of clumsy anyway. Okay? So you can compute as many terms as we want for this. Any questions so far? Okay, so let's do the other one. If C0 equal to 0 and C1 equal to 1. What is C2 again? C2 is always 0. For this particular example. Okay, so in this case, what would be C3? C3 is 0. C4 is 0. Sorry, did I mess up? This is 1, sorry. This is 1. C1 is 1 for this case. Okay, so C4 is related to C1. Okay, this is for n equal to 2. Okay, so it's minus C1 divided by 4 and 3. Negative 112. C5 will be 0. Are we still okay, guys? It's very tedious. Are we okay? What is C6? What do you think? Are you guys all lost?
C6 is 0, right?
C6 is 0, yeah. C6 is 0. So all this column, the whole column is 0. Okay, C9 will be 0, all these are 0. Okay, C2 is 0, C5, C8, all these are 0. Okay, C11, 0. Okay, so what will be C7 then? C7 is related to C4. It's negative of this guy, which is going to be 112 divided by 7. So this is 4 and 3. So this will be 7 and 6. Okay, 7 and 6. This will be 1 over what is 12 times 42? 1 over 502. Is that correct? Yeah.
504, right?
Huh?
Is it 504?
Yeah. 504. 504. 42 plus 12. Yeah. 504. Yes. We can do one more, I guess. What will be C? The next one here is C9 is 0, C10, C11 is 0. What is C10? C10 will be negative now. Divided by, instead of 7 and 6, will be 10 and 9. Negative 1 over 90. Okay. Is that right? Is that right, guys?
45,000.
Huh?
45,360 is the answer.
45. No. Okay. Okay. Okay, so I have now y2. Okay. I basically have y2 now. So y2x is going to be I don't know where to write it. Can I write it here? I just run out of space. Okay, so y2x will be all these are 0, all those are 0. What's C1? C1 is the coefficient of x. Okay, C4 is the coefficient of x to the power 4. This is coefficient of x to the power 7. That is the coefficient of x to the power 10, and so on. So those are my y1 and y2. Those are the two fundamental solutions. Okay. At the end, the general solution, okay, the general solution is going to look like this. General solution. It's going to be y equal to C0 y1 plus C1 y2. Okay, and if you want to write it out, it will be like this. Will be y equal to C0 times that whole chunk plus C1 times that other chunk. Do I have to write it? Okay, I'll write it. 1 minus 1 over 6 x cubed plus 1 over 180 x to the power 6 minus 1 over 19800 x to the power 9 and so on plus C1 x minus 1 over 12 x to the power 4 plus 1 over 504 x to the power 7. Okay, that's the answer to our question. I'm going to let you think about it and ask some questions before I explain why we can assume that.
Well,
Shelby, are you going to say something?
yeah. Well, I was wondering why. Are you able to hear me?
I can hear you. If you cannot, if your mic doesn't work, just type it in the chat.
Okay. I was just wondering, could we have solved for Cn minus 1 instead of Cn plus 2 for the recurrence relation?
Mm-hmm. We solve for, we just iteratively do this. So they are 3 apart. From C0, I'll get C3, C6, C9, and so on. From C1, I'll get 147. These are
Oh, okay. So it's possible either way.
So for this particular example, it's not always like that. It's a little bit crazy, the computation, but I just want you to understand the general procedure. Anyone has any other question? Before I try to explain why you can assume these things. Okay. Okay. I'm going to leave that recurrence relation there. Okay, so it's the not. I actually did do something like this before, but you probably don't remember it. Okay, you can take a look at this. This result comes from linearity. I actually did do this a little while ago in chapter 4. But I can show this to you again. Why? If you want to. Unless you remember all the stuff that I did before, which is unlikely. So do you want me to show you why this is true?
Yes.
You can scale and add together solutions and we'll make another solution, right, for a linear equation?
So it's basically you can do linearity. Basically, you can call this thing. I'm going to, notation-wise, I'm going to make it a little bit easier so that I don't have to write that much. I'm going to call this LD of Y. Okay, it's a linear operator, operate on Y. Are you guys okay with this notation? LD means, so LD is actually, this LD thing is just D squared plus PX D plus QX. And that will be my LD. Okay. I'm just using this notation now so that I don't have to rewrite this again and again. So LD is a linear operator operating on Y. Okay. So we know that LD of Y1 is equal to 0. Okay, because it's a solution, right? It's a solution. LD of Y1 equal to, okay. And Y1 0, because the Y1 satisfies the initial condition. This is equal to 1, and this guy is equal to 0. We also know LD of Y2 is equal to 0, and Y2 0 is equal to 0. Y2 prime 0 is equal to 1. Okay. So what will be LD of AY1 plus BY2? Now this guy is going to be, because it's linear, you can just operate inside. It will look like this. But this guy is equal to 0, and this guy is equal to 0. So it's A times 0 plus B times 0, so it's equal to 0. Okay, so this guy is going to be a solution of this. But does it satisfy the initial condition? Let's see whether it satisfies the initial condition. A, Y1, Y2. At 0, we want to make sure it's equal to A. It is equal to A because this will be A times Y1 at 0 plus B times Y2 at 0. But Y2 at 0, Y2 at 0 is going to be 0. Okay? Y2 at 0 is going to be 0. Y1 at 0 is 1, so this one is just A. It's exactly what we want. And for this other one, Y2 prime of 0 will be AY1 prime 0 plus B Y2 prime 0. And this guy, Y1 prime 0, Y1 prime 0 is 0. The other one is going to be 1. So this guy is equal to B. So it does satisfy the initial condition. So all this is saying is that it's because of linearity that we have this result. Okay? Because of linearity, we have this result. Are we okay for now? The next thing, if you're okay with this, I have shown you this before. Then the next thing I'm going to show you is that this A is actually our C0, and this B is actually our C1. And why is that the case? I'm going to show you this, okay? I'm going to show you this. But I just want to make sure that you don't have any question up till here. Okay, if not, I'm going to show you this.
Can you not erase for like 20 seconds?
Okay, I'll just wait for a little while. 20 seconds, okay.
Thank you.
Yeah.
So you said this is the same thing as what we did quite some time ago, right? Like,
Yeah, I showed you this result a while ago.
is it the exact same thing?
Yeah, exactly.
Okay.
Not the C0 and C1 stuff. I mean, this thing I did show you once when I talk about linear operator. When I was doing a preview for chapter 4.
Yeah, I remember that.
Okay. Talia, can I erase now?
You can erase the top portion.
Top portion, but I don't want to erase the top.
Oh, okay. Then it's fine.
Then I'll wait a little bit until you're ready, okay? Let me know though, okay, Talia?
Okay, like 10 more seconds.
Okay.
You can erase.
Okay. Oh, this will erase so much. Okay, that's fine. Now remember the solution look like this, right? Okay. So when we say y0 equal to a, y0 equal to a, can you see y0 equal to a means when you put in 0 here, when you put in x equal to 0, okay? When you put in x equal to 0, can you see that this is the same as C0 equal to a?
Yeah.
When you put in x equal to 0, all these are gone. Okay. How about y prime? Y prime is going to be C1 plus 2C2x plus 3C, 3x squared and so on. Y prime 0 is equal to b. It's the same as C1 is equal to b. So basically what it is saying is that this guy here is y0. The constant term is y0. This term, the coefficient of x, is actually y prime 0. Okay? Okay? So that is why, so basically here, y0 is equal to a, y prime 0 is equal to b, right? So this guy here, so this whole chunk of stuff is basically saying that the first line here is saying that C0 is equal to 1, okay? C1 is equal to 0. Here is C1, C0 is equal to 0, and C1 is equal to 1. So this is correspond to this. You remember we were doing this earlier. We assume this and get one solution. We assume this and get another solution. We get the y1 and y2, and then we do a linear combination of the y1 and y2 with the a and b, which is C0 and C1. I hope I explained this to you by now. And that is why, because of this, what we can do this. Because of this, we can assume C0 equal to 1 and C1 equal to 0, okay? And then we can use recurrence relation to get y1, and then we assume the other way, C0 equal to 0 and C1 equal to 1, and we use the recurrence relation, and you get y2. And your final answer is your final answer will be y equal to C0 y1 plus C1 y2. Okay, and this is the A and B. The C0 is A and C1 is B.
For assuming C0 equals 0 and C1 is equal to 1, shouldn't you be finding y2?
Oh yeah, that's y2. Thank you, Anna.
Yeah.
Thank you. Is it okay? This is what we did earlier. Too bad the board is so small, I just have to keep erasing stuff and can keep everything on the board. So we are going to do more examples. Don't worry about it too much yet, okay? So we are going to do more example, and because you see the first example, and it's going to be easier later. Any questions so far? I am going to do a variation of this. You guys okay? Okay. So the original problem that we did for this was like this. We are trying to solve y double prime plus xy equal to 0. Okay. Now, if we put in an initial condition, y0 equal to 3 and y prime 0 equal to 2. So if we do something like this, okay, we already have the general solution, right? We have the general solution. And then we have, usually the way that we did it before was that using this guy and this guy, and then try to solve for C0 and C1, right? You guys remember that? But we already know that this guy is actually C0. This guy is actually C0. This guy is actually C1. So you can just put this 3 into here and 2 into here, and then you will get your answer. You guys know what I'm talking about?
Are those the initial conditions
Yeah.
that were given?
Conditions. Because we say that this one is actually C0, right? We just explain it, and this one is actually C1. So your actual answer is going to be just change the C0 to 3 and C1 to 2. Another way to do this, to think about this, is that from this recurrence formula, okay? Now, if here, you can also start out with this C0 equal to 3, C1 equal to 2, and C2 equal to 0, and then use this relation, okay? And then use this relation. And then just keep iterating, and you'll get the same answer. Do you guys know what I'm talking about? Kind of. Okay, so I think maybe the best thing is to do another example. I don't know whether I have enough time to do another example though. Let's try then. Okay, I'll try to start another example then, okay? It's not very much similar to what we have, but it's just a little bit different, okay? So how does this look like? The ordinary form. Okay, so y is equal to summation Cnxn n equal to 0 to infinity. So what would be y prime? 1 to infinity and Cnx n minus 1. Y double prime will be n equal to 2 to infinity and n minus 1 Cn x n minus 2 y double prime minus 1 plus x y equal to 0 will be this guy. Is it so far so good? I'm going to distribute this. And then we need to do some replacement stuff for these two guys. Are we okay?
I think we're okay. It's just a lot of writing.
Okay.
We're fine.
Okay. Okay, we do some replacement stuff. So what do we replace it by?
First one, n equals n plus 2.
This one is going to be n plus 2. Now this one is already xn, so we don't have to do anything. And this one will be n minus 1. And replace n minus 1. Now you can combine all this together. Okay. You can combine all this together. Now, but this guy start with 0, this guy start with 0, this guy start with 1. Okay. So you have to separate out the n equal to 0 term here. Okay. So when you do that, when n equal to 0, you will have, when n equal to 0, n equal to 0, this one will be 2 times 1, C2, okay, minus this guy n equal to C0. So it's basically 2C2 minus C0. That will be the constant term plus all the other ones. Okay, hopefully you follow that. So what do we have here? We will have 2C2 minus C0 equal to 0. And then we will have this, n plus 2, n plus 1, Cn plus 2 minus Cn minus Cn minus 1 equal to 0. This is for n big equal to 1, 2, 3, 4. Okay, so we end up with C2 equal to 1/2 C0. Okay, and then this recurrence relationship is going to be Cn plus 2 equal to Cn plus Cn minus 1 divided by n plus 2, n plus 1 for n equal to 1, 2, 3, 4. So we're going to stop here, and then next time we start from here. Okay?
So the next steps are like the assuming parts.
Yeah. Next step is going to assume. Yeah. we're going to assume C0 equal to 1 and C1 equal to 0.
And the other way around as well, right?
And then the other way around, and then you get your y1 and y2. Yes.
Thank you, Professor.
Okay, you're welcome. Is it okay, guys? I'm sorry, this is a little bit hard. It's just very tedious.
It's a lot, but we'll get used to it.
Yeah, you just need to do some of the homeworks. Yeah. I didn't even assign that much homework, actually. Only like 3 or 4 problems. Maybe I should have assigned a little bit more, but I already assigned it, so it's there. But each of them is pretty long, though, in terms of getting it right?
Yeah, these will be pretty long.
Okay, so any other thing you want to ask or any other comment? Is it really hard to do this online like this?
It's getting easier the more you get used to it.
Yeah, it's fine.
Okay, so in that case, I'll see you on Thursday then, okay?
All right, thank you.
Thank you.
Thank you, Professor.
Thank you.
Okay, you're welcome. Bye-bye.
Great day. Stay safe.
Bye.